All right, let's get right into it. Have you ever really stopped to think about how your computer is juggling a dozen things at once? It's not magic, not at all. It's actually a super well-coordinated dance. And today, we're going to pull back the curtain and see exactly how all the different parts of a program talk to each other to get things done. So here's the best way to think about it. Your computer isn't one person working on one thing. Nope. It's really a whole team of workers, all doing their jobs at the same time. We call that concurrency. But, just like any team, if the workers can't communicate, you don't get a masterpiece, you get pure chaos. And that is the million-dollar question, right? How do you stop one worker from jumping the gun before another one has the data ready? How do you prevent two of them from trying to grab the exact same tool at the exact same moment? You need rules. You need a system for communication. That leads us perfectly into our first section. The official name for this whole system of rules is inter-process communication, or you'll just hear it called IPC. This is basically the playbook that lets all those different tasks buzzing around on your computer coordinate their work.
So yeah, IPC is just the set of tools your operating system gives you to manage all this chatter. And just a quick heads up on the name, interprocess kind of sounds like it's only for separate programs, but it really applies to any unit of work. Could be a process, could be a thread inside a process. It's all just about tasks talking to each other.
So how do they actually talk? Well, it pretty much boils down to two main strategies. You can either have everyone share a common space to leave things for each other, or you can have them send direct messages back and forth. Let's break down what that looks like.
Okay, first up is shared memory. The best analogy is a shared refrigerator in a house full of roommates, right? Anyone can put something in, anyone can take something out. It's a common, shared space. That's shared memory. On the other hand, you have message passing. This is more like writing and mailing a Christmas card. It's a specific piece of info packaged up and sent from one person directly to another.
Now here's where it gets really interesting. This is the classic trade-off. Shared memory is blazing fast because the operating system doesn't have to get involved every single time. But that's also its biggest weakness. It can be super error-prone. I mean, what happens when you and your roommate both go for the last slice of pizza at the same time? You get a conflict. Message passing is a bit slower because the OS has to act like the mailman, but it's way, way safer. And big bonus, it can scale across different computers, not just the one you're on.
This line from the philosophy behind the Go programming language just nails the modern way of thinking about this. The trend these days is to favor the safety and the clarity you get from message passing. It forces you to be really explicit about how things communicate, and that almost always leads to stronger, easier to debug programs.
Okay, so if we're all in on message passing, what are our options? Well, it turns out there's a whole toolbox for this. Let's take a look at 3 of the most common tools you'll find for the job.
The 3 big ones you're going to run into are pipes, message queues, and sockets. You can kind of think of them like a wrench, a screwdriver, and a hammer. Each one is designed for a very specific kind of communication job.
First up, we've got pipes. And honestly, the analogy here is just perfect. Imagine a water pipe. You drop a rubber duck in one end and it flows out the other. Data only goes one way, from a writer to a reader. It's simple, it's direct, and it's fantastic for situations where one task is just constantly feeding data to another one.
Next up, message queues. This is like a shared to-do list for your whole team. New tasks get added to the list, and any worker who's free can just grab the next one in line. The key word here is decouples. The person creating the tasks has no idea which worker will do the job, they just toss it onto the queue. This is incredibly powerful for building systems that are flexible and can scale up easily.
And finally, we have sockets. Think of a socket as a dedicated phone line between 2 tasks. It takes our Christmas card idea to the next level. You're not just sending one card, you're opening a connection so you can have a full-blown two-way conversation. And the real magic of sockets is that they're so flexible. They work just as well between 2 tasks on opposite sides of the world as they do on the very same machine.
All right, so we've looked at the individual tools. Now, let's see how they come together in one of the most useful and powerful patterns in programming, the thread pool.
The idea here is simple, but it's absolutely brilliant. See, creating a new thread for every tiny little task is actually pretty slow and wasteful. A thread pool gets around that by creating a bunch of worker threads right when the program starts and then just reusing them. They hang out in a pool just waiting for work to come their way.
And this is how it works. See how it all comes together? Each worker thread in that pool is just stuck in a simple loop. It waits for a job to pop up in a message queue. When one does, it grabs it, does the work, and then immediately goes back to waiting for the next one.
That message queue becomes the central traffic controller for the entire pool of workers.
Okay, theory is one thing, but let's see what this actually looks like in the real world. We're going to use this thread pool pattern to tackle a classic computer science problem, cracking a password.
A lot of times, cracking a password is just a brute force effort. You have to check every single possible combination. That's a huge job, but here's the thing. It's also perfectly divisible. We can break down the millions of combinations into smaller chunks. The main thread just creates these chunks and drops them on the message queue, and our thread pool gets to work, with each worker grabbing a different chunk to check.
And here's the payoff. Check this out. Just running this job on one single thread took about 52 seconds. Which, isn't terrible. But by unleashing a thread pool with multiple workers all tackling different pieces of the problem at the same time, we got it done in just 17 seconds. The difference is just staggering.
That's the bottom line. By using the right communication tools, a message queue to coordinate a whole pool of worker threads, we didn't just get a small boost. We got more than a 3-time speed up. Just let that sink in for a second.
And that really just leaves us with one final thought. We've seen how having the right communication strategy can turn a bunch of separate tasks into a super high-performance team. So the question I have for you is, if you could make your own projects 3 times faster, or smoother, or more responsive, what kind of amazing new things would that let you build?